Okay, thanks for coming, everyone. I'm Kiron Lebeck, and today I'll be talking about our work on securing augmented reality output. This was work done in collaboration with Kimberly Ruth, Yoshi Kono, and Franzi Rosner at the University of Washington. So let me start by explaining what we mean by augmented reality. So we define augmented reality, or AR for short, to broadly encompass computer-generated sensory feedback that is overlaid directly on a user's perception of the physical world. And to give you an example, many of you have probably seen this, and if you haven't, this is Pokemon Go, a smartphone-based AR app that was immensely popular last year and was one of, if not the most popular mobile games of all time. But simple smartphone apps like this barely scratch the surface of augmented reality's potential. We're seeing rapid advancement from simple AR apps on devices like smartphones to more sophisticated devices. For example, headsets like Microsoft's HoloLens, or AR-enabled car windshields from companies like Hyundai and Toyota. And these emerging AR technologies show great promise across a wide variety of domains, ranging from gaming to navigation and on-road assistance, to education and medicine, and also to military applications. Essentially, there are numerous application domains where AR shows great promise, and a big part of that is the increasing ability of these technologies to support dynamic, immersive content. And this capability is enabled by a couple of key features unique to AR systems. One, their abilities to continuously capture and process sensory input from a user's surroundings. And two, their abilities to generate sensory feedback and blend it directly with a user's perception of the physical world. Unfortunately, the same features that make AR so powerful also leave it in a uniquely privileged position to negatively impact users' privacy and security. And so there remains a critical gap in knowledge here. What are the threats facing AR users, and what can we do about them? And to contextualize this work, it will help to understand what an AR system of today typically looks like. So at a high level, AR applications receive and process sensory input, such as RGB, audio, or depth information from a user's surroundings. And they generate sensory output, such as audio, visual, or haptic feedback. And so far, the security community has predominantly focused on input privacy defenses, and there's been some really great work in this space. And one of the promising defense strategies that has come out of this body of literature involves incorporating a trusted input module as part of the OS of an AR system. And the role of this module is basically to enforce least privilege on applications. It takes in raw sensor streams, filters those streams in some way, and extracts higher-level information that it can then dispatch to applications. And so while it's not the focus of our work here, we'll leverage ideas from this corpus of literature as needed. So now we're going to switch focus to the crux of this work, which is output security, and specifically visual output security. So I'll start by motivating the need to consider output security at all, followed by a discussion of Arya, an AR operating system that we designed with mitigating output security risks as a first-class goal. I'll then briefly cover our initial prototype and evaluation, and I'll conclude with some potential future directions for AR researchers and designers. Oh, excuse me. Wow. To start, to give you some intuition about the kinds of problems that we're dealing with here, we want something like this, where 3D objects can be seamlessly integrated into a user's perception of the physical world. For example, a Pokemon like this level 36 Charizard here. But what we don't want is a situation like this, where applications clutter a user's view of the physical world with some sort of undesirable content. And in particular, we consider how to defend against buggy or malicious applications that may intentionally or inadvertently augment a user's view of the physical world in undesirable or harmful ways. So for example, by obscuring another application's virtual content in order to hide or modify its meaning. In this AR windshield example here, that would be the speed overlay. By obscuring important real-world content, such as pedestrians, or by disrupting the user physiologically, such as by startling them or triggering seizures in people with epilepsy. And so the question we ask is, how can we enable the operating system of an AR platform to play a role in mitigating these kinds of output risks? And to answer this question, we designed an AR platform with output security as a first-class goal, which we call Arya. And designing this kind of platform with this goal in mind is challenging for a number of reasons. For example, what kind of information would the OS need about application state to prevent undesirable or harmful behaviors? And in what ways can the OS visually constrain output at all? The first observation, which we made in a prior workshop paper, is the following. Traditional displays, like those used on PCs, employ the window abstraction for displaying content, where applications receive access to some bounded, often rectangular region of a display, within which they can draw arbitrary content. And this is great for isolating application outputs on systems like PCs. However, this abstraction is not natural for AR, where in the future, we might want multiple applications to display dynamic content that simultaneously moves all about a user's world. For example, a virtual dog or a virtual Russell Wilson, shown here. Furthermore, Windows do not allow the OS to understand anything about the content that apps are displaying, only the regions within which content may be displayed. And so, in our workshop paper, we propose the following. The AR object abstraction, which would allow the OS to understand and manage virtual content at the granularity of individual objects rather than the coarse granularity of Windows. And so in this work, we build on the AR object abstraction, and we introduce the Arya operating system. Unlike existing AR systems, Arya is designed to support multiple applications simultaneously, augmenting a user's view of the world, and is to our knowledge the first system to do so. To give the OS a more active role in constraining output, Arya includes a trusted output module as part of the OS. Arya also includes an input module, as prior work has suggested, not only to filter sensor information available to applications, but also to generate an understanding of a user's underlying environment and feed this information into the output module. For example, by detecting pedestrians. And the primary role of the output module is to interpose on application requests to display or modify virtual content according to policies or behavioral constraints on AR objects. And so a key component of our work centers around the numerous questions surrounding policies. So the first question we considered was just what is a policy, or what kinds of things should policies generally do? The general notion of behavioral constraints alone is quite abstract. And to get some inspiration, we drew on some existing sources that we thought might provide good starting points and adapted them to an AR setting as needed. For example, various automotive guidelines concerning road visibility seemed appropriate for an AR setting, such as not obscuring road signs or pedestrians. And the HoloLens developer guidelines also provide suggestions on behaviors that AR apps should generally avoid. An important note here is that the HoloLens guidelines are not technically enforced. They're merely suggestions. In Arya, we can enforce such guidelines. Furthermore, these guidelines tell us only what conditions should be met, but not what to do when those conditions are violated. Thus, our approach for expressing policies is to define them as essentially if-then statements containing both a conditional predicate as well as a mechanism or action that Arya should take on objects when a policy's condition is met. For example, one way we could turn the abstract guideline of don't occlude pedestrians into a policy is by saying if an object is occluding a pedestrian, then make it transparent. This construction allows us to specify policies in a well-defined manner, but it also raises some interesting questions, such as what types of actions should mechanisms take? And additionally, consider the following policies. One takes more transparent objects and makes them opaque, and one takes more opaque objects and makes them transparent. And while these are sort of contrived examples, they showcase an interesting challenge, which is what happens if multiple policies enter a cycle where they keep triggering each other. We call this event a policy conflict, and a key design challenge was figuring out how to address such conflicts. Ultimately, Arya's goal is to keep users safe and secure from the output of malicious or buggy applications. And one way to do this is to bring the AR user's view of the world closer to an unmodified view of the real world. For example, by making objects smaller, more transparent, or slower. And so we define policy mechanisms as essentially intrusiveness bounds on objects. For example, setting a maximum opacity, a maximum speed, or a maximum size. In other words, we make our policies composable by design. When evaluating policies on an AR object, Arya takes the set of minimally intrusive transforms and applies them. So in the paper, we discuss a number of additional design challenges and decisions involved with designing a policy specification framework. and enforcing policies, which I won't have time to go into here. However, we consider the identification of these challenges a contribution in and of itself, as they represent major hurdles that AR system designers must address if they wish to incorporate ideas of output management. So now we'll take a brief look at our prototype and evaluation. Our primary goal in prototyping Arya was to iteratively drive our design process, but there are a couple of challenges to prototyping a new sort of AR system. For one, no existing AR platforms, to our knowledge, support multiple immersive applications running at once. And two, AR systems depend heavily on sensors and sensor processing techniques, so they must contend with noisy input from the real world. While improving sensor processing techniques is a very important field, it's orthogonal to our work, so we don't focus on it here. And so to get around these challenges, we use the Unity game engine to essentially simulate real-world environments. For example, we have an AR car windshield scenario that we mocked up here. And this has a couple of key benefits. First, having a fully specified underlying world allowed us to reliably repeat experiments. And second, this approach gives us the option to inject varying levels of input noise deterministically to simulate imperfect sensors. For the purpose of this work, we didn't inject any additional input noise, but this sort of test environment enables that option for future work. Essentially, we replaced the real world with deterministic Unity environments, and we used a desktop PC rather than a real AR device to display output. Our applications also ran as separate processes that communicated with our Arya backend over local sockets. So here we have our three scenes intended to represent some real-world AR scenarios. We have a home scene, an automotive setting shown before, and an office setting. Next, we built multiple applications for each of our scenes, and they all mimicked some amount of behavior that could be considered malicious or buggy. For example, in the home scene, a game that's running on the coffee table also pops up an annoying in-game purchase dialog, and another app blocks the user's vision by tethering a spider to the center of their view. In the automotive setting, the user has an app that displays push notifications, but it displays them even when the user is driving. And the user is also being bombarded with advertisements. And in the office scene, we have some people that are working on a 3D car modeling project, but their application is buggy and goes a little bit out of control, taking over their view. Additionally, a helpful colleague identification app happens to obscure too much of the user's view here. So first, let's take a look at our home scene. Among the policies enforced here are one that prevents objects from one app from occluding content displayed by another app. So in this case, the in-game purchase sign was actually blocking a virtual cat displayed by another application, and you can see a transparency artifact where that pop-up was removed. Another policy says avoid headlocked content, or objects that appear at a fixed location in the user's display, which caused the spider to be removed. And finally, although you can't really tell from a still image here, another policy prevents objects in the scene from moving too abruptly and disorienting the user. Next, in the driving scene, Arya successfully removes the ads that are blocking the pedestrians in the road, while still allowing other ads to be displayed on designated billboards. It also removes the user's push notifications while they're driving, which is, again, hard to tell from a still image here. And finally, in the office scene, our prototype policies significantly declutter the user's view of the world, removing spurious objects that fill their view, and it also ensures that application content remains at a sufficient viewing distance from the user, a policy taken from one of the HoloLens developer guidelines. And our final policy prevents objects from obscuring an exit sign in the top right, which could pose a safety hazard. So we successfully translated a number of abstract guidelines drawn from various sources into enforceable policies that our prototype applied to multiple applications in a variety of scenes. And while these policies are not intended to be an exhaustive list, they serve as a concrete starting point for reasoning more broadly about AR output security. So finally, I want to step back and look to the future. Now that we have begun to explore the AR output security space, where do we go from here? And there are many possible directions. For example, our work further supports the need for better handling noisy sensor input. If an AR system cannot create an accurate representation of a user's environment, it will not be able to intelligently manage application behaviors. Additionally, while our policy specification framework serves as a great starting point, incorporating more complex policies and constraint solving could further extend policy expressiveness. And finally, it will be critical to involve end users in the design of any sort of AR output management tools. A policy enforcement framework that needlessly infringes on users' abilities to function smoothly in their AR environments would represent a major hurdle to adoption. So in conclusion, this work takes the first steps towards addressing the fundamental challenge of securing output in augmented reality systems. And a key part of this was the design of Arya, an AR operating system intended to mitigate the risks of malicious or buggy application outputs. We developed a policy specification framework that serves as a great starting point for exploring more sophisticated output management techniques in the future. And through the iterative design and implementation of our prototype, we demonstrated the feasibility of Arya, which we used to surface lessons and recommendations for future efforts in the AR security space. Thank you for your time, and I'm happy to take questions.
Thank you for this. I think it's the first time I've understood this subject at all. The graphics help a lot. What bothers me a lot about this is I'm not exactly sure that this is any kind of a foundation, because the human visual system is extremely complicated, and you don't seem to have any psychologists or physiologists working on this. So I'm not at all convinced that these even slightly getting at the object, the point of human safety in AR, which seems to be a very cool thing, but you know, I don't see where this is going. And the idea of my visual system just being a place for apps to put ads is it's not a future that I'm asking for. Yes, especially while I'm driving, and these days even while I'm walking. So where do you really see this going? Do you think the human visual system perhaps should be totally replaced?
Yeah, I think you raise a couple of very interesting points. Your first point involving like psychologists and people that have a better understanding of human physiology, I think that will be absolutely critical for future work. We need the technology to be at a place where involving those kinds of people actually serves a useful purpose. If the systems are too abstract, then asking for concrete feedback on sort of physiological things I think is going to be too challenging. So we need this sort of technical foundation just at a system level to even get there. You also raised an interesting point about not asking for a future where your vision is filled with ads, and I think that's absolutely true. I don't think any of us would ask for that, but I think we may get there because of monetary incentives by companies and whatnot. So even though that's not a future we wish for, I think it's something we need to plan for and try to defend against in some way.
Next question.
Nathan Downhorn from UPenn. Very cool work. This is exciting. OS abstractions for AR. So have you considered some of the real-time constraints, right? So you've got a lot of the algorithms and in certain static overlays, you can really kind of precisely say stuff. Did you look at like delay of the algorithms and all this stuff at all?
Yeah, so we had a very basic performance evaluation that demonstrated that the sort of output techniques that we were using currently didn't impose too much overhead, but I think for a real system, when you have actual sensor input that's incurring more overhead and stuff like that, figuring out appropriate latency and delay is going to be really important. So yeah, that's definitely an avenue for more work.
Thanks.
Yeah.
Saurabh Bakshi from Purdue. You showed that your entire OS is not a trusted computing base, but only parts of it. So I worry that as you increase your policy specification and the mitigation actions, does the attack surface for your solution increase to the point where it becomes an issue?
I think that might have been just a graphical failing of conveying what's trusted and what's not. I think one of the interesting avenues of potential attack has to do with where policies are coming from. So who is implementing policies, who's specifying them. And figuring out the right set of actors for that, I think, is going to be really important, and that's also an avenue for future work.
Right. Thank you.